Hi, so welcome to this other lesson on linear transformations in linear algebra. So here what we are going to do is to show that if you have a vector, so let V and W be vector spaces and let T such that V maps to W be linear. So T here is a linear transformation. If B is equal to these set of vectors is a basis for V, then R of T is equal to the span of T of beta. Like beta here, I said B earlier, but it's beta. Beta here is the set of all the linearly independent vectors that span V. Okay, when we say something is a basis, I've really done a lot of videos about these things. When you say something is actually a basis for a vector space, okay, it means it spans that vector space. Then R of T, this is also a set, is equal to the span of this. That is also a set. So it's going to be, what I'm going to do is that to prove this, we want to show that for any element in this, the R of T, that element also belongs to the span of T, T of beta, and then for any element in the T of the span of this T of beta, then that element is also in the R of T. Now let's start with this. So we want to show this. We want to show that R of T is a subset of span of T of beta and also span of, so this is how you show that two sets are equal. The span of this side is going to give you a lot of set, like it's a set. The span of T of beta is a whole set and R of T is also a set. So to show that two sets are equal, you want to show that each one of them is a subset of the other. So the span of T of beta here is also a subset of R of T. It doesn't matter which one we show first, but so long as we're able to show these two things, it means these two sets are equal. Okay. Now let's start with the span of T of beta. Now notice that what we are going to notice is that for little vi in beta, so beta here is the set. So for each one of these v's you pick in the beta, what is T of beta? T of vi. T of vi, since every vi is in capital V, because let me start from that place as well. We also know that this vi belong to capital V because beta is a subset of capital V and it's the basis. So for every element you pick in the beta, is also that element also belongs to the bigger V. Okay. Then T of vi belong to the range of T. That is one thing we just did in our previous video, that the range of T is defined to be the transformation of all the vectors in capital V. So every vector you pick in capital V, when you transform it, you get it in the range of T. Okay. So what does this mean? It means that and we also know that the range of T is a subspace, right? That was the earlier video we did as well. It means for any scalar multiple or for any two vectors you pick, this also shows that since we know R of T is a subspace, for any scalar multiple of T of vi, right, this also belongs to the range of T. And then again, if you pick the sum of different ones, maybe, so example, so we can do this, C1 T of V1 plus C2 T of V2 belongs to the range of T. And these are all coming from the idea that the range of T is a subspace. We've done this earlier. So what does it show you? It shows you that what is the definition of the span of T of beta? T of beta is actually the span of these guys, T of V1, T of V2, all the way to T of Vn, right? What is the definition? The definition of this is this linear combination of all these elements here, and then we are trying to say that the linear combination of these elements belong to the R of T. It means that the span, every element you pick, so for let's say we can pick any element, we can actually write it like U belonging to the span of T of beta, for every element you pick in that span, you also belong to the range of T. What it's trying to say is that the span of T of beta here is a subset of the range of T. So we are done with one part of the subset inclusion. Now the other part is to show that for every element you pick in the range of T, that element also belongs to the span of T of beta. Okay, so now let W belong to the range of T. What can we say? Then there is this some V or maybe some U that belong to capital V, right? These are vectors, such that, because before you can get the range of T, you have to transform some vector in V, okay, such that T of that U is equal to W, right? So now let's look at this. What is U? U is a vector in V. Then what can you say about that U? U, since V has the beta as its basis, right? Any element that belong to V can be expressed as this. So U is equal to the linear combination A1 capital V1 in of the vectors in beta, A2 V2 plus all these things AN VN, which can be simplified as or maybe you can just leave it like that. Okay, so U is equal to that. Now since T is linear, right, since T is linear, what can you say? Let's take W. W is what? W is equal to T of V, T of U, which is equal to T of A1 V1 plus A2 V2 plus all the way to plus AN VN. And in this case, since T is linear, you can say this is A1 T of V1 plus A2 T of V2 plus all the way to AN T of Vn. What is this trying to say? What is this definition? What do you have here? This is exactly the definition of the span of beta, the span of T of beta. So it means this is equal to, we can write it in a compact form, which is summation as I start from 1 to n AI T of Vi, right? And this is the linear combination of all the vectors T of V1, T of V2, T of V3, all the way to T of Vn, right? So this belongs to the span of T of beta, because all these V1, V2, all the way to Vn belongs to beta. Okay, so what does it say? It says that for an element for W in R of T, it means that W belongs to the span of T of beta. And if you have two sets and you are saying that when I pick an element in set A, that same element belongs to set B, what does it mean? It means that set A is a subset of set B, right? So this means R of T is a subset of a span of T of beta. So we've been able to show that the span of T of beta is a subset of R of T. R of T is also a subset of the span of T of beta. What does it mean? It means that this means R of T is actually equal to the span of T of beta, with the beta defined. All right, beta is actually defined, that beta is equal to V1 V2 all the way to Vn, and this is the basis for how do I call it, capital V. So now this gives us a ground to find the range of T when you are given a linear transformation, right? So in our next lesson, I'm going to pick an example that will guide us to find the range of T straight away without going through all the stress we did in some of the previous videos that we did. Okay, all that we need to know is the basis of the vector space we are actually performing the transformation from, and then we can get a range of T straight away. All right, see you.